Welcome to an introduction to spheres. So let's look at 2 dimensions and then we can talk about something in 3 dimensions. So a circle is the locus of points in a plane that are the same distance from a point called the center of the circle. And we've been graphing circles, right? We would graph a center point and then to graph our circle, we would draw our radius in 4 different dimensions, and they would all be all those points with the exact same distance from that center point. So every point on the above circle is the same distance, in this case from the origin, because our center happens to be the origin, in the xy plane. So this is a 2-dimensional plane. Now imagine that you took that circle and you started spinning it, and it went around and around and around. And so now it's no longer 2 dimensions, it's in 3 dimensions, and you would have our sphere. So a sphere is the locus of points in space that are the same distance from a point. So here, instead of being in 2 dimensions, we're in 3 dimensions. So now this isn't 0, 0 anymore. This is, let me write in a different color so you can see it. This is actually the point 0, 0, 0, because we have 3 dimensions. We have the usual right, left, up, and down that we're used to, but now we have 3 dimensions, so we can go out from the center as well. So if we were to spin that 2-dimensional circle, we would have a sphere. Right? So here's our 3-dimensional sphere. You might notice these circles going around. I'm going to kind of outline one of them. So I'll outline this one. And these sort of look like ellipses, but they're representing circles. That's what happens when you take something that's 3-dimensional and you have to represent it on a 2-dimensional surface like a smartboard. So these are called the great circle. And as you might be able to figure out from the name, it's the largest circle in the sphere. Right? So if I were to go around the widest part, and there's actually an infinite number of these great circles, they all go though around the widest part, which means that both of these endpoints here are on a diameter. So this is a diameter. A great circle that you're familiar with, if you think of the Earth or a globe, the equator would be a great circle. If I were to go from the North Pole around the Earth to the South Pole and back again, that would be a great circle, right? Because those endpoints would be on diameters. Right, so we're going to be dealing with a 3-dimensional sphere. And let's learn a little bit more about a sphere. So spheres are 3-dimensional closed surfaces. A sphere is a set of points in a 3-dimensional space equidistant from a point called the center. The radius of a sphere is the distance from the center to the points on the sphere, just like the radius of a circle is the distance from the center to points on the circle. Spheres are not polyhedra. Right? Polyhedra have only polygons for faces, and there's no polygon on a sphere. It's all round. Right? So it is not a polyhedra. Here we have a sphere. Right? And so here we have an example of the great circle, and let's kind of outline that. So the great circle goes around the widest part of the sphere, right? And the endpoints of a diameter are on the great circle. If I go only halfway from the center to the edge, that would be a radius. So that would be a radius here. So the blue here is a radius, and the red is the great circle. And here in green, I'll outline a diameter. And you have this very same diagram in your notes. Okay. And I think it's pretty well labeled. You might want to just maybe draw an arrow from the great circle to where it's located on the sphere. Okay, so you have this in your notes. I'm going to add just a little teeny bit on the bottom that's not in your notes. And I think it'll help you understand how to find, first of all, surface area on a sphere. So of all the shapes, a sphere has the smallest surface area for its volume. So if you were looking for a cheap packaging container, the sphere would be it. It uses the least amount of materials, and it can pack in the most amount of stuff for any of our solid figures. The only problem with a sphere is it would not make a very good packing container because, well, your packing container would roll away. But if it wouldn't roll away, it would be a great, and it doesn't stack very well either. So other than those two problems, it would make a great packing container. You'd save some money on materials. So to understand the volume formula for a sphere, you have to understand the surface area formula for a sphere. So this is one of the few, this is the only shape where we're going to start with surface area rather than volume, because the volume formula won't make any sense unless you understand the surface area formula. So to see how the surface area of a prism is derived, imagine a sphere is wrapped in a piece of paper. So we're going to use the prism to help us understand the surface area of a sphere. Okay? So imagine here I have this piece of paper, this rectangle. So this is my piece of paper. And I'm going to wrap it around the sphere. Okay? Just like I have over here. So here I've just wrapped up the sphere in the paper. So if I look, if you remember the area of a rectangle, it's length times width. Right? So this would be the length, and this would be the width. I guess I'll write up and down. Okay. If you would, under that, in your notes, there's a little bit of space there. Maybe just draw a small rectangle like this and label it length and width. Okay. Now, the length, and I guess I'll just mark it up here. This length here corresponds, so the length on the paper that's all stretched out, laid flat, corresponds to this distance here for the piece of paper that's wrapped around the sphere. And the width of this piece of paper is the same as this distance for the paper that's wrapped around the sphere. All right, so area of a rectangle is length times width. Well, now let's think about what the length and width are for the paper that's wrapped around the sphere. And what does that have to do with the sphere? Right? So here, I'm going around the sphere. I could draw it here. I could also draw it here, but I think it's harder to see it. Right, that would be the same. I guess I should have put it in red so it matched the one up here. Oops, there we go. I'll just draw it in red. So I have it up there just because it looks three-dimensional up there. But I could draw it here as well. Right, so, or I could draw it over here. So what is that in relation to the sphere? Well, if you think of when we were learning cylinders, right, we're going around a circle. Now it looks like an ellipse just because this is two-dimensional. But if you imagine the paper is wrapped around the sphere, I'm going around a circle. Well, what is it when I go around a circle? What's that called? Well, we have a special name for the perimeter of a circle. Perimeter of a circle is called circumference. So the length of my paper is the same as the circumference of the sphere. And how about the width of my paper? Right, this green distance here. Right? So, well, I'm going from the bottom of the sphere to the top of the sphere. I have it drawn over here, but I could have just as easily put it right there. Well, if you're looking at the sphere, you notice that that would be the diameter, right? That's the diameter of the sphere. So this green line here is the diameter. And what's another way I could represent diameter? Well, diameter is the same as 2 times the radius. So let's replace the width in my equation with 2 times the radius. Right? And so I'd like you to write that part into your notes. It sort of has it above, but I think this is a little clearer the way I have it written here. So just put that in a little space there. We'll have enough room. Now let's replace circumference and radius with the formulas. All right, so how do we calculate out circumference? Well, the circumference of a circle is 2 pi r. Right? How about 2 times the radius is just 2r, right? Well, what if I multiply those together? Right? So I have 2 times 2, that's 4. I got a pi, and I got r times r, and that'd be r squared. And guess what? That is the formula for the surface area of a sphere. 4 times pi times the radius squared. And that's how it's derived. Imagine we just wrapped up a piece of paper around our sphere, so it was exact same height as the sphere, and it went all the way around the sphere, and we unwrapped it, we'd realize that that paper there represents our surface area of our sphere. And the length of our sphere would be its circumference, and the width would be the height of the sphere, which is the radius, 2 times the radius, or the diameter. And actually, we have one other formula. And so I said that we also could represent this as diameter. I may as well show you the other formula. So I'll just do this one, I guess, in blue here. So the length is still the circumference, right, for the other formula. And we have the width, which is, instead of 2 times the radius, I could also represent that as the diameter. Right? So 2 times the radius is the exact same thing as the diameter. And so there was one other formula for circumference. Remember, we had 2 pi r. The other one was pi times d. And so this is the area. So I'm going to replace circumference with pi d, the other formula for the circumference. And then, of course, diameter, that's just d. Now, if I multiply that together, I get pi times diameter squared. And that's the other formula. So these two formulas are absolutely equivalent, because the diameter squared, let's put it up here, is the same thing as 2r squared, right? Because diameter equals twice the radius. And if I square 2r, okay, 2 squared is 4, and r squared is r squared. So diameter squared and 4r squared are the exact same thing. So you could use either one of these formulas for the surface area of a sphere. Let's do one problem together so that we can, and I'll use both formulas. All right, so I wanted to show you how this formula came about, right, because I want the formulas to make sense. If they make sense, you'll remember them and you'll understand them. And then, secondly, I wanted us to practice a couple. So here are the two formulas for surface area, 4 pi r squared and pi diameter squared. It doesn't make any difference to me which one you use. You can switch back and forth. You can use one or the other, whichever you prefer, right? They are equivalent to one another. So this problem is in your notes. It's at the very top of the page. So we're going to find the surface area of the sphere with a radius of 14 centimeters. And I'm going to use both formulas. Right? So surface area. So let's identify our radius and diameter. Those are the only dimensions in a sphere. Right? So the radius is 14 centimeters. The diameter would be twice the radius. So our diameter is going to be 2 times 14, or 28 centimeters. All right, so if we use the first formula, surface area is 4 pi r squared. The surface area of our sphere would be 4 times pi times 14 squared. Right? And 14 squared is 196. And then we would just multiply that by 4. And that would be, so if this were 200, 4 times 200 would give me 800, but this is 4 less. So I've got 4 times 4 less, so this is going to be 800 minus 16. I just don't have a calculator handy, so I wanted to show you how I can do some of these in my head. I make it a little bit easier problem. So 784 pi centimeters squared, because this is area. Okay? Let's do the same thing, but let's use the other formula. Right? And so the other formula we have, and I'm just grabbing a calculator, is 28 squared. I don't know off the top of my head. I know 14, but not 28. We have the other formula, we're going to use pi times 28 squared. All right, so when we square 28, we should get 784, assuming that I didn't make any errors on the other side. And I do get 784. So that would be 784 pi centimeters squared. So you see, either one of these formulas can be used, whichever you prefer. Right? Sometimes the numbers are a little bit larger for the squaring, and so I don't always know them off the top of my head. And if I don't have a calculator handy, sometimes I find the first formula easier. But you can always use the second formula as well, whichever one you like. All right, so that's all I'm going to show you in this podcast. In class, we'll look at some more problems with the sphere and the hemisphere. And so the hemisphere is just, I had that actually, I believe, on, and I didn't even mention him. See on the last page? There he is. I didn't even mention him. I just so focused on the sphere, I didn't even write here hemisphere. And so you have that one in your notes. So a hemisphere, you just take a sphere and you just cut it in half, and you have a hemisphere. The hemisphere has only one great circle. It's right there at the bottom, right? Because that's the only diameter is along the bottom. Everything else, lots of radii, right? So this would be a radius. And so from the center up here, that would be a radius, but only one diameter, so it only has one great circle. So we'll look at the formula for the surface area of the hemisphere in class, and we'll also look at how the surface area, the volume formula for a sphere is derived from its surface area formula. Right? So we'll see that in class. Right? So that's the end of the podcast. Thanks for watching. Bye.